Okay, welcome back to Electrical Science and Principles, okay? And our heading is going to be transformers, the transformer. Not the transformers on TV, okay? But the transformer for current or voltage, okay? Right, the transformer. These are just things for you to do based on the information I'm hoping to provide you with. And you can come back and try and answer some of these yourself, okay? Ignore this is no longer applicable to this because this figure here has changed, but the knowledge is still relevant and still the same, okay? Okay. The transformer, principle of operation. Let's go into it, make sure you can see it fully, okay? Okay. That's your iron core, okay? V1, V2 out, okay? Now all transformers use electromagnetic induction discovered by Michael Faraday as their principle of operation. When a conductor is cut by a magnetic field, an EMF is introduced into the conductor. The basic transformer consists of two electrically separate coils wound onto a common ferromagnetic core. When one winding is supplied from an alternating current source, a magnetic field is set up which is also alternating. Okay? It means that the field rises and collapses at given intervals. The changing magnetic field links with the second coil via the iron core, resulting in an induced EMF. The coil in which the current is flowing is called the primary, and the one into which the EMF is induced is called the secondary. Excuse me. Now, in this application of Faraday's principle, the changing current which produces the magnetic flux is flowing in one circuit, and the induced EMF appears in the second coil, which is electrically separate. This is called mutual induction. Since the magnetic flux set up by the primary winding current will link both windings, then an EMF will also be induced into the primary. This EMF is due to self-induction. For both windings, the induced EMF will depend upon the number of turns on the coils and the rate of change of the magnetic flux. Okay. And we have the main core, okay? The rate of change of magnetic flux will be the same for both primary and secondary windings. Therefore, the EMF induced into each turn will be constant. Assuming no losses occur, then E1 equals V1 and E2 equals V2, where E is the induced EMF and V is the terminal voltage. It therefore follows that the ratio of voltage to turns for each winding will be equal to V1 over N1 equals V2 over N2. Now we rearrange this. V1 over V2 equals N1 over N2 gives equation 1, i.e. the voltage ratio is equal to the turns ratio. Okay? Okay, when load is connected to the secondary winding, a current now flows in this winding. If we continue to neglect the losses, then we can say that the input power will be equal to the output power. Therefore, V1 I1 equals V2 I2. Rearranging this expression gives V1 over V2 equals I2 over I1, equation 2. Combining equation 1 and 2 will therefore give V1 over V2 equals N1 over N2 equals I2 over I1. Okay. Since the assumption of no losses was made, when deriving the above statement, then this ratio is sometimes called the approximate transformer ratio. In practice, power transformers are very efficient devices, therefore the ratio above will give reasonably accurate results in practice. And here I've simply given you an example. I've not given you the end result to it, but that's for you to work out and have a little play at. Okay. And again, example 2, similarly 2, 3, and 4. Okay. That again is for you to work out and have a play at for yourselves. And here we have transformer construction. Now let me just go into here. So you can see the construction for yourself. Okay. Core type. The coils are pre-wound using copper wire, and then the laminated iron core is built up around them. Notice that the iron does not completely surround the coils. Figure 2. And that's your figure 2, okay? It is usual to split the primary and secondary winding between limbs, the windings being arranged concentrically. Okay? And you will see that in figure 4 as we move forward. Alternatively, the windings may be split into several layers which are sandwiched together. Okay? These methods of winding the coils lead to improved magnetic flux linkage between the two windings. Okay. And here we have the shell type transformer. Okay. Shell type. Okay. Just go and make sure you can get the viewing. Okay. In this construction method, the coils are wound onto one former, but the sandwich principle may still be used. It should be noted that the iron core provides a complete path around the coils. This helps to reduce the amount of magnetic flux which does not link with both windings, leakage flux. Okay. You can see the end of the primary winding and end of the secondary winding. Okay. Let's make sure I can get this in. Okay. Okay, yes I can. Okay. I'm just moving. Okay. In both construction types shown in figures 1 and 2, the wire used for the coils has a covering of insulating varnish to prevent adjacent turns from shorting together. Following construction and testing, the transformer is heated to expel moisture and immersed in insulating varnish. This process fills the voids within the windings and secures the conductors so that they do not move due to magnetic forces. Okay. And here we have our iron core. Okay, iron core. The magnetic circuit iron core is built up from thin sheets of steel. By this process, the effect of eddy current losses in the iron is reduced to an acceptable level. Eddy current is the subdued magnetic effect you get from passing a current through any conductor, and you need to eliminate eddy current, otherwise you will create a lot of heat wherever there is eddy current. So it's important that eddy current is kept to a minimum. The steel used for the lamination has about 3% silicon added to it. This helps to reduce the hysteresis loss, which is produced in the core. The core is assembled using T and U shaped pieces, each layer being separated by a thin layer of insulation applied to the metal. The bolts which clamp the core must not short the lamination, otherwise they will be heated due to eddy currents and cause a more problem for the transformer. Okay. Power transformers are constructed so that the heat produced by losses in the winding I2R and the iron losses can be effectively removed. If this is not done, then the increasing temperature will lead to a breakdown of insulation and ultimate failure of the transformer. The diagram at figure 7 shows how ducts are built into a transformer so that the coolant can get down to the bottom layers of the coils. Okay, figure 7. Okay, cooling duct maintained by longitudinal spacers. Okay. Figure 8 shows a transformer fitted into a steel tank. The tank has pipes all around its side, okay, and that is this one here we're looking at. Okay, heat from the transformer is absorbed by the oil, which raises its temperature and causes it to rise by convection. It will then flow down the pipes where air can circulate around them to remove the heat. The use of the pipes greatly increases the surface area available for cooling. The cooled oil re-enters the tank at the bottom and the cycle continues. This type of cooling process is known as ON, oil cooled natural air. It is commonly found on distribution system transformers. Other cooling methods are AN natural air cooling, OW oil immersed water cooling, OB oil cooled forced air, AB air blast, or a combination of these. Okay. This is just the technical data, okay? The following is a typical schedule for a 100 kilovolt amp transformer. The performance figures quoted below are those for normal ratio with a mean winding temperature of 75 degrees Celsius. These figures would be guaranteed by the manufacturer to the tolerance permitted by BS 171, 1978. Now bear in mind that with the standards may have changed in regards to joining the Europe, and it also may have changed again when we left the EU due to Brexit. Okay. Terminal block of a star delta transformer, okay, and here you can see what we're looking at basically, okay. Firstly, okay, that's all star connection, okay, shows you how it is connected to the block, and that's all delta connection here, okay. Basically delta is series wound, star is, you can look at it from the point of being parallel wound basically. Note that the primary winding delta is labeled using capital letters A, B, C. The secondary is identified using lowercase letters A, B, C. A small y is used for the star point. Okay, that's where the cables meet. This is an auto transformer, and auto transformers consist of one tapped winding which forms both primary and secondary. The main advantage of this device is the saving in materials used for its construction, and the major disadvantage is the direct electrical connection between the input and output. It is this latter reason which results in the application of such devices being limited by the wiring regulations to situations where no danger can be caused should the common section of the winding become open-circuited. If such a situation arises, then the input voltage will appear at the output terminal. And that's the danger of that. You don't want 2000 volts coming out, going in here, and 2000 volts coming out there. That would be highly dangerous to yourself. The auto transformer can commonly be found in some types of fluorescent lamp circuit and in the starting of induction motors. It is also used in transformer for the grid system. Assuming no losses occur, then the previously established formula for transformer ratios can be used for auto transformers calculations. Okay. Instrument transformers. Okay. When measuring high values of voltage and current, it is common to use instrument transformers to reduce the value to be measured to a level that can be safely handled by the instrument. To measure high voltage, a voltage transformer VT is used. This is a double wound transformer made with a suitable ratio. For example, to measure an 11,000 volt supply with a 110 voltmeter, a VT with a ratio of 100 to 1 step down would be required. For current measurement, a current transformer CT will be used. In this device, the primary carries the current to be measured and the secondary carries a proportionately lower current value. Most CT have a bar primary. This is usually the conductor or bus bar carrying the current to be measured. The secondary is a toroidal wound coil, a coil wound onto a iron ring. Okay. The load current sets up an alternating magnetic flux which is in proportion to the load current. This flux cuts the turns of the coil, inducing an EMF which drives a current through the attached instrument, and we call it the burden. Okay, and this is what it would look like basically. Okay, overall, we just come back a bit to make sure we can get it all in. Okay, and that would be your picture of it there. Okay. Okay, we'll come back. We'll come right back. Okay. Now, in the power transformer, a secondary load is necessary to cause a primary current to flow, which maintains the magnetic flux in the core at a constant value. With a CT, the primary current is in the load circuit and will flow whether the secondary is connected or not. The secondary current through the ammeter is necessary to stabilize the core flux, and if the ammeter is removed, the voltage across the secondary terminals could reach a dangerously high value and cause insulation breakdown. The CT must never be operated with secondary terminals open circuited. If the ammeter must be removed from the CT, then the terminals must first be short circuited. One side of the secondary is normally earth. Okay, and that is all instrument transformers. Clip on ammeter or tongue tester. Okay, that's what this is here. Okay, tongue tester. The clip-on ammeter, figure 1.3, uses the same principle as that described on page as above. For the current transformer, the laminated core of the transformer can be opened and passed around a single core cable. In this way, a measurement of the load current can be made without disconnecting the supply. The diagram shows an analog scale, but digital types are also available. Many tongue testers also have a built-in voltmeter as well. Okay. And here are some questions for you to look at. Now again, I would suggest you answer these questions proficiently for yourself, as it is practice for you to do. Okay. Okay, here you are. Okay, and that is your work done for you. Okay, gentlemen, ladies, and those of you who may be something else, no offense intended and no disrespect to anyone. Okay, But that is it. Thank you for your time and have a good day. Let me just make sure I've worked my way back so I've got everything in and everybody can see the work that they need to do and what we're talking about, hopefully. Okay. And that is us. Thank you. The transformer, and we are here. Okay, thank you for your time. Have a good day. Bye bye.